Okay, thank you. Let me first thank the organizers for inviting me. It's a good chance for me to talk about these non-standard methods in Ramsey theory and combinatorics of numbers. Okay, so as we all know, there are areas of combinatorics where very diverse techniques have been applied. And recently also the methods of non-standard analysis have been applied in this discrete context of combinatorics. Usually a non-standard analysis is applied in the continuum, but it can also be applied in the discrete. And mainly in two areas. An area of additive combinatorics about density-dependent result, meaning results about sets of integers that are large in the sense of asymptotic density. And also in the area of Ramsey theory. And there is this book in preparation. If people is interested, there is an overview of some of the applications we found with these non-standard methods. Now, this talk will be mainly about the role of hypernatural numbers in Ramsey theory, because they can be used in a way as ultrafilters. And we all know that ultrafilters are central in certain areas of Ramsey theory. Now let me just quickly review what I mean by non-standard analysis. For the purpose of this talk, you don't need to know much, just this rough idea that you have a sort of uniform way of extending the mathematical object you are interested in to their non-standard extension or hyperextension. And this extension is a sort of weakly isomorphic copy in the sense that it is an elementary extension, meaning that all elementary properties, meaning first-order properties, are preserved. So there is no way of distinguishing the two structures by means of elementary properties. And the basic principle is called, in this area, transfer principle, which means that whenever you have an elementary property of certain objects, that property is true if and only if it is true about the corresponding non-standard extensions. And for instance, since the integers are a discretely ordered ring, and that is a first-order property, the non-standard extension, the hyperintegers, would be a discretely ordered ring. And similarly, the hyperreal numbers will be an ordered field, but it is an extension, so it will properly extend the real line, and it will be a non-Archimedean field. So just to make one very easy example, the property of ordered fields, since they are elementary, first order, they are preserved. Other properties that talks about subsets, like the well-ordering property of the natural numbers or the completeness property of the real numbers, of course, are not. Okay, let me point out one thing. The ultraproduct construction is familiar in certain areas of mathematics, and let me tell you that non-standard analysis in some sense is just a uniform way of dealing with this ultraproduct construction. And in fact, the basic construction one has for this hyperextension is just by taking ultrapowers. So really quickly, I'm not talking about the continuum, as I told you, but just to give you an idea, the hyperreal line is a non-Archimedean proper extension of the real line, and with additional property, because as I mentioned, the transfer principle holds. Of course, it is not a complete field, but we can do several things. We have the infinitesimal numbers there, meaning non-zero numbers which are smaller than 1 over n for all n. And of course, conversely, we also have the infinite numbers. And a fundamental property we have on the hyperreal line is this fact that if you have this hyperreal line, you will have the positive infinite number, the positive negative numbers. The other numbers are called finite, and each of them is infinitely close, meaning that the distance is infinitesimal, to a unique real number. And that is called the standard part. So you have the infinite numbers, and all numbers here are, each of them is infinitely close to one single real number, called the standard part. We will focus more on the discrete, so let's have a look at the hypernatural numbers. Almost all of you, I believe, are familiar with non-standard model of the natural numbers of Peano arithmetic. So you have an initial segment that is exactly the same as the usual natural numbers, and you have the infinite numbers. Now, because of transfer, you have several additional properties. For instance, you have that every hyperreal number has an integer part in the sense that it is between one hyperinteger and the successor, and other similar properties. Another class of really fundamental objects in this area is the class of hyperfinite sets. That is a crucial point because it is a notion that is in between the finite and the infinite. So formally, as far as first-order properties are concerned, they behave exactly as finite sets. On the other hand, they are infinite objects, and we will see that we can apply other tools that are more typical of the infinite objects. And the typical construction, if you want to have an idea, is just to take an ultra product of larger and larger finite sets. So let me sketch briefly why we think that the methods of non-standard analysis can be of use in combinatorics, and I believe that there is still much to be exploited in this direction. As I mentioned, we have this nice feature that the hyperfinite setting can accommodate arguments of elementary finite combinatorics. So you can do some finite combinatorics in there on one hand. And this can be applied also to infinite sets. And typically when we study properties of sets with positive asymptotic density, they are infinite set, but we can, in some sense, use them as finite sets. And this is experimental. When we found some non-standard proof for density-depending result, exactly the same argument works exactly in the same way for amenable groups, for instance. It's a general construction. And the third point is something that I really would like to exploit much more. I think it's a very interesting bridge, the non-standard setting, between the discrete and the continuum. I will give you one easy and short example of this phenomena, but I think that this is a direction that should be considered. And in fact, as I mentioned, there are tools from the continuum, typically from measure theory, or for instance, like Birkhoff-Ergodic theorem, Lebesgue density theorem, that can be used in the hyperfinite context of hyperintegers. So we can apply there both the methods of finite discrete combinatorics and the powerful methods of analysis or ergodic theory. Now, what I will mention mostly in this talk are the role of ultrafilters in Ramsey theory, and we will see how the hypernatural numbers can replace the use of ultrafilters, simplify the formalism, and produce also some new result. I will present a few of them. And at the end, as we all know, non-standard analysis was born from model theory, because it's a study of special class of non-standard models of the real numbers and of the natural numbers. And so we are in a model theoretic setting, and we have, for instance, saturation, and we can apply also other tools from model theory in this context. Okay, let me just start with, say, level 0 non-standard analysis. The first thing that one do is to accommodate some of the notions in this non-standard setting, and usually these are really close to the intuition we have. For instance, in this area of combinatorics, the notion of thick set and synthetic set are central. And thick set is a set of integers containing arbitrarily large intervals. And in a non-standard setting, one simply says that there is an infinite interval, meaning an interval where the two edges have infinite distance. And synthetic set, which is sometimes called generic in model theory, it means that with finitely many shifts, you will cover the whole group, And that is the same as to say that there are only gaps of some bounded length inside the set. And the non-standard version is exactly that. It has finite gaps, because finite is a notion we can use. We have finite numbers and infinite numbers. So every infinite interval will meet the non-standard extension of the set. Another notion that is really important in this area is obtained by combining syntheticity and thickness. And this is an important class because it is partition regular, contrarily to thick set and to synthetic sets. And a piecewise synthetic set is an intersection of a synthetic set and a thick set. And in a non-standard setting, one can say that a set is piecewise synthetic if I can find some infinite interval, and I look there, the non-standard extension of star A over there will have only finite gaps. So let me give you two examples of, say, non-standard reasoning. This is sort of level 0 non-standard reasoning, meaning I'm just taking the definition in the non-standard setting, and I think sometimes this simplifies the argument and make it more direct. So for instance, if you want to prove the partition regularity of this piecewise synthetic set, let's see this for two partitions. It's really easy. I take the non-standard extension. It is split into blue and red elements. Now there are two possibilities. If the blue elements of star A only have finite gaps, then it means that the set blue is piecewise synthetic, because we found this infinite interval where we only have bounded gaps. But if this is not the case, it means that it must have an infinite gap, meaning that there will be an infinite interval with no blue element. Now, looking at this infinite interval, I will only see red elements. So the original set and the red set will be the same on this infinite interval, which means that on that interval, the red elements have only bounded gaps. So red is piecewise synthetic. And that's exactly the intuition we have in the usual proof of these kind of properties. Now let me give you a say, level 1 argument. There is a notion that one uses is called Banach density. It's a generalization of the usual asymptotic density. In asymptotic density, one considers only initial segments and take the relative density over there and take a limit. Here we just fix finite finite n, and we look at all possible intervals of length n, and we find the one where we have the largest number of elements, and we take the limit of that. So of course there will be sets with 0 asymptotic density and Banach density 1, so it's a much more general notion. And in a non-standard setting, this means that we have an infinite interval somewhere where the relative density up to infinitesimals is exactly the Banach density. Now we can work on that hyperfinite setting, and we have tools. A typical tool from non-standard analysis is the lobe measure, which is a measure that extends the so-called counting measure. Counting measure means that since we are working on a hyperfinite setting, to several extent, it's just like working on a finite set. So we have simply the ratio of elements we have divided by the number of elements. We have this counting measure. And if we take the standard part of this, we get a finitely additive measure on the collection of so-called internal subset. I mean, the nice subset that one can consider in non-standard analysis. And there is this canonical way of extending it to a genuine measure that's called the lobe measure. Now we can consider this operator, the shift. Remember, we are on a hyperfinite setting, so we are working just like on a finite set, and we can consider the shift operator.
Sorry,
yes?
So in the second, it doesn't matter which interval you get, you will always get this
No, there must be one.
There is only one.
Well, actually, there are infinitely many, but
Which one you take? If there are several, you should get the same density?
yes, it's possible that you have several, you get the same density, yes. The largest possible density you get, that will be the Banach density. If you take all possible infinite intervals, the largest possible will be the Banach density. Now we can apply Birkhoff ergodic theorem. And so we have that almost everywhere with respect to this measure, we will have this limit to exist. So now let's have a look. What does it mean taking that limit? That limit, as you see, is you take the non-standard extension of A for almost all point xc. If you look at the copy of the natural numbers xi, xi plus 1, xi plus 2, and so forth, I mean, this is just a copy of the natural number. If you look over here, the actual asymptotic density will be that limit. Now, because of the definition of Banach density, which is the largest possible relative density we get on an infinite interval, that limit has to be precisely the Banach density of A. So this means that we have many copies of the natural numbers, starting from almost every psi, where the non-standard extension has an asymptotic density which is exactly equal to the Banach density of A. So this, what is the meaning of this going back to the property of the original set? Well, this is a property that is finite embeddability. It means, well, we say that a set B is finitely embeddable into A if any finite portion of B has a shifted copy inside A. This means that the combinatorial richness of B can be recovered inside A. And this is important in this area of combinatorics because preserving finite configuration is relevant. For instance, if we have that B contains arbitrarily long arithmetic progression, then also A will have the same property if we have this finite embeddability property. Now, by what we proved before, we get this result that is well known. I mean, I'm not saying that this is something new, but actually we get much more than this. But one get immediately that if we have a set with Banach density alpha, we have each of these sets will have the same genuine asymptotic density and will be finitely embedded into the original set A. And actually, one can prove in this direction much more. For instance, one can have sets with a Schenemann density alpha that can be finitely embedded into the original set. This means that if we want to prove some combinatorial property, we can, without loss of generality, assume that we have the Schenemann density equal to alpha, not just the Banach density, which is a much weaker notion. Okay, this was just one example. And now let me go into the ultrafilter business. Now this is the central observation. If we are working in a non-standard model of the natural numbers, if we take every point corresponds to an ultrafilter, because we can take all the subset with the property that that point belongs to the hyperextension of that. That is the same as considering the one type of the element psi. And so in some sense, if we have enough saturation, we can take points in our non-standard model as ultrafilters. And then we should use them. Okay, let me just make a remark. Some people don't like ultrafilters because they say they come from the axiom of choice, because they never saw one. But actually, you can find one. And you can actually buy one for, say, $100 online easily. So there are ultrafilters after all. Okay, let's work with this ultrafilter. We have this notion of equivalence between points. That is simply the fact that two points are equivalent if they generate the same ultrafilter. This means that these 2 points cannot be distinguished by any standard property. For instance, the 2 points, if they are equivalent, they will be both even or both odd. For instance, they will both have, I don't know, an even exponent of 2 when you factorize them, or any property you can think of, they will satisfy the same thing. Let me remark you that this notion was already considered when non-standard analysis was much popular than now, and nice properties were proved by using this idea, for instance, about the Rudin-Kiesler ordering or other similar properties. These are 3 of several papers that can be found. Now, we have a topology, a natural topology on this set of natural numbers. And the topology is the so-called standard topology or U topology, and it's the topology having as closed set all these hyperextensions. Now, this space is similar in many extent to the Stone-Church compactification to the space of all ultrafilters. And in fact, a quotient of it is isomorphic to the set of all ultrafilters. But let me tell you that, okay, Stone-Church compactification is in some precise sense is the largest possible Hausdorff compactification of the discrete space of the natural numbers. This space we have now, the hypernatural numbers, is an even larger space, but still it satisfies nice property. For instance, it is compact, it is completely regular, although not Hausdorff. The natural numbers are dense in it. We have the universality property that every function from n into a compact Hausdorff space can be extended to a continuous function. And this can be seen by using characterization of compactness that one has in non-standard analysis. And since we have this star map, any function we have on the natural numbers has a canonical extension, a non-standard extension. And for instance, as we know, on the hypernatural numbers, we have a commutative sum and a commutative product that we do not have on ultrafilters. Now, let me mention an additional thing that we will be using, and this is tricky to many. I mean, it takes some little time to get used to it, but one can iterate this non-standard extension. And this fact of iterating the non-standard extension has applications, as we will show. So we have the natural numbers. We have that the natural numbers are an initial segment of the hypernatural numbers. We write down this first order property. Then we go to the second level non-standard extension, and we will get that the hypernatural numbers are an initial segment of the hypernatural numbers, and so forth. So this looks like a game, but it's a formalism that I will use shortly. Okay, just to give, again, this is, of course, something that can be proved by using the counterpart with ultrafilters, but it's just to illustrate the use of this iterated extension. So let's take Ramsey theorem. So it's not by chance that combinatorics and logic are linked together, because the original Ramsey theorem was proved towards a result in logic. So this is the non-standard proof with iterated extension. So we have a finite coloring, say, of the pairs, to make it simple. We take the pair Ni star Ni, which is one of the many possible pairs we have on a hyper natural number. It will belong to one of the pieces. And since we have that property, by transfer we find an element so that the pair H1 and Ni belongs to star C, because that's how the transfer works. The property we are using is that there exists an element such that the pair of that element with star of Ni belongs to star star C. Now the same property by backward transfer will tell you that there must be some H1 so that the pair H1 and Ni belongs to star C. And again, starting from the two properties just proved, and again using transfer, we can find an element H2, which can be taken larger than H1 because this Ni is infinite, so that we have that the pair H2 Ni and the pair H1 H2 belongs to C. And we can iterate the process and find this homogeneous set. And similarly, one can prove this more generally for K tuples. Now, of course, this is just the, say, non-standard counterpart of a well-known ultrafilter proof, but this shows you how to handle these things. Now, a central operation we have on ultrafilter that produced many applications in combinatorics is the so-called pseudo-sum. It is defined like that, and we have that a set belongs to U plus V if and only if the collection of shifts of A by N belongs to U, belongs to Ni, to V almost everywhere in the sense of U. So we take this shift, and we will show you briefly that this operation is really important because the idempotent elements with respect to this operation will produce several interesting combinatorial properties. Now, how this sum between ultrafilters is related to the sum we have on the natural numbers. Of course, they cannot be the same because the operation we have on the hypernatural numbers is commutative, while the operation on the space of ultrafilter is highly non-commutative. But here the iteration of non-standard extension help in the sense that make things simple. If you want the sum between the ultrafilter generated by Ni and by me, you just take the element Ni plus star Ni, which is essentially different from Ni plus me. Now, how one can use this? Well, first of all, let's focus on the idempotent ultrafilter. The existence of this idempotent ultrafilter takes Alice's lemma, which requires repeated applications of Zorn lemma and the compactness of the space. And with our characterization, to be an idempotent element is the same as to say that the element Ni plus star Ni is equivalent to Ni. Another property that is equivalent is that whenever we have a set A and Ni belongs to star A, then it means that a shift of Ni by some element of A is again inside the same set. Okay, let me show you a proof of Hyndman's theorem, but with this formalism. Is just by using idempotent ultrafilter. It was an important discovery that by using this ultrafilter, one could simplify much the original combinatorial proof. And starting from that, Hyndman himself and other researchers followed that direction of using the algebra on this space of ultrafilters and produced several results in combinatorics. And this is the proof how it goes. I mean, it's not a simplified proof. It's the actual proof with non-standard things. We take an idempotent element. By the characterization, we have one element x1 with the property that x1 plus Ni belongs to the non-standard extension. And then by induction, by using the property that Ni and Ni plus star Ni, they are equivalent. and by using transfer, you see the formalism at this point, once one is used to it, it's really simple. This is one example. Of course, one can generalize this and towards other theorem in this direction in Ramsey theory, like Milkamp-Taylor theorem or even Gauer's theorem can be proved by using this technique in a simplified way. But let's try to go to some genuine new result to make one example how this can be used. And the subject now is that of the partition regularity of Diophantine equations. What does it mean? I mean, we have an equation, and we say that this is partition regular. If we have the property that that equation has many solutions, in the sense that whenever I finitely partition the natural numbers, I always find monochromatic solutions. So there is a celebrated theorem that goes back to 1918, I think, Schur theorem, that says that in every finite coloring of the natural numbers, there are monochromatic triples A, B, A plus B. This is just a straightforward application of Ramsey theorem, but at that time it was a central point in proving that Fermat's last theorem was false in arbitrarily large finite fields. And Schur theorem can be rephrased by saying that the equation x plus y equals z is partition regular. Now, by using another important theorem, van der Waals theorem, stating that in any finite coloring one finds arbitrarily long arithmetic progression which are monochromatic, and by just reducing to consider the three-term arithmetic progression, one finds that the equation x plus y equal to z is partition regular. Of course, the point is that not all linear equations are partition regular. There are easy examples. And an important theorem of Rado gave a complete characterization in very simple terms. If you have an equation, linear equation of the form Ci xi equals 0, sum of that form, you have that it is partition regular if and only if a partial sum of the coefficient equals 0. So for instance, if we go back, this is true for the Schur equation and for x plus y equal to z, but it's not for x plus y equal to 3z. Okay, let's go to the non-standard viewpoint, and we have that partition regularity simply means that one can find equivalent non-standard points that are solutions. So indistinguishable points which are a solution to the equation. Okay, let me give you one example that will be used afterwards. This is a side remark by Bergerson and Heinemann in a paper of theirs. If one takes an idempotent ultrafilter and take this sort of linear combination, one obtains that every set in that ultrafilter contains a three-term arithmetic progression. And in this way, one can give an alternative proof of the partition regularity of that equation. Now, I noticed that in non-standard terms, this can be rephrased in that form. You take these 3 points, you see that they form a three-term arithmetic progression. And since these 3 points, they are equivalent because of the property of idempotency of Ni, by transferring back 3 times from the hyper extension of the natural numbers to the natural numbers, we get that every element in the ultrafilter generated by these 2 Ni plus Ni, we get a three-term arithmetic progression. So starting from that, one can find a completely standard general result that can help proving the partition regularity of equation. So take the finite strings and say that they are equivalent. Take the smallest equivalence relation containing the empty string, which is considered to be equivalent as 0. If you repeat something, then you will be equivalent to the previous thing, and it is coherent with concatenations. So for instance, these two sequences are just the same as 1, 3, 7, 4 because they are obtained by putting some zeros here and there or by repeating numbers. Now we have this relation is precisely what is needed in order to have that two linear combinations of idempotent are the same. So if one wants to forget about the non-standard thing and just prove some simple standard result, one could say that two polynomials are equivalent if the string of coefficients, they are equivalent in that sense. And then one can prove the following, that if we are given some polynomial and we want to prove that that polynomial is partition regular, a sufficient condition is the following. We find polynomials P1 to Pk which are equivalent in that sense, meaning that they are obtained by taking this sequence of coefficients to be equivalent. And then if those polynomials are such that when one substitutes into the variables of Q, one obtains 0, in some sense they are solutions, then this means that the original polynomial Q is partition regular. So if you want, if you look at the previous example with the equation x1 minus 2 x2 plus x3, the three-term arithmetic progression, one simply consider the polynomial 2 plus x squared, 2 plus x squared, 2 plus 2x plus x squared. And one find out that they are equivalent and they satisfy the polynomial Q. So by using this technology, one can give an alternative ultrafilter proof of Radon's theorem, for instance, by simply combining in a suitable way this ultrafilter. If one try to do this directly, it will get a messy computation. But with this kind of formalism, everything is much more simple. And another equation that, for instance, one can show that it is partition regular is this one. This was recently proved by Moreira and Bergelson, and it took a very heavy machinery. And I'm not showing you the details, but it's just a three-line proof by using that characterization, because one finds equivalent polynomials which are a solution of this. There is recently much interest in finding out the partition regularity of equations similar to this. I will show you why. So I'm not going into this computation. How much time do I have?
10 minutes.
Okay, so let me, these are just computation, really easy ones, just to find the right coefficients. Okay, let me just give you one example. We have this equivalence between points, and we can use some of the properties of this equivalence. So if 2 points are equivalent, you take any function, any standard function, and they will go into equivalent points. Now, one of the nice properties that one can use is property 3 that corresponds to an ultrafilter property, the one that is written below. If I have that the image under a standard function of a point is equivalent to that point, then one necessarily have that that image is precisely that point. Now, this has consequences if one wants to prove partition regularity. Well, I think I skipped that. No, it's here. Okay. Let me skip this for a moment and let me show you this. Just to give you one easy example, for instance, this was not known to be not partition regular. And that's the way that the argument works. We assume by contradiction that it is partition regular, and we have 3 equivalent points satisfying that equation. Since we are working with hypernatural numbers, we can do almost everything we are doing with natural numbers. So we can factorize alpha, beta, and gamma. We take out the greatest exponent of 2. Now, the exponent of 2 of a number is the image under a function. So it means that if alpha, beta, and gamma were equivalent, also these exponents are equivalent. Now, these 3 numbers are equivalent and they are even, cannot be odd. So these exponents are positive. And we distinguish 2 cases. If A is less than B, then we factor. And we find out that 2 times the exponent A must be the same as C. Now, C is equivalent to A. But since the function double applied to A is equivalent to A, this actually means that they must be equal. So 2A must be equal to A, and this is a contradiction. And the case 2 is similar. It uses a very easy trick. If A is equal to B, since we have that equality, and since alpha 1 and beta 1 are odd, the sum of their squares is congruent to 2 modulo 4. This means that we can factor out one more exponent in 2. And similarly as above, we have that 2 times A plus 1 is the same as C, which is in turn equivalent to A. And this means we get also in this way a contradiction. This is one example one can. I don't have much time now. There are new results that, let me skip this, about the nonlinear case. There are many open problems in this area. These are some of the recent results that I found on the direction of not partition regularity. And let me skip this. Could be technical, but let me mention that the result we found as corollaries have results that have been proved one by one and by different techniques and with much more work, I think. Okay, this is another recent result that generalized Rado's theorem. And let me just mention this corollary here. If we have a linear part and a nonlinear part, then one can prove that these kind of equations are partition regular if and only if the Rado condition holds on the linear part. By using, here we have to combine 2 different techniques. The technique that I mentioned before to prove that something is not partition regular, and the technique to prove that it is actually partition regular, but this takes considering special ultrafilter and manipulating them. We did it in a non-standard way, but one can also do it in a standard way. And also we have that these kind of equations, they are partition regular, provided that Rado condition is not satisfied. And we have several examples that one can have. And as I mentioned, some of the known results can be recovered as corollaries of these general results. For instance, the equation x minus 2y equals z squared, and so forth. And here starts a new field of configuration. One can ask what kind of configuration are partition regular, what are not. This is sort of endless thing, but one can try to classify precisely what is partition regular and what is not. So let me close. I have 3 minutes, okay, with some open question. The first one is about idempotent ultrafilters. They are central in several areas of combinatorics. The only known proof is by using Ellis lemma, which takes 2 times the application of Zorn lemma. So the natural question is, the axiom of choice really needed in its full power? and recently we proved that having the property that every filter on the continuum can be extended to an ultrafilter, that is enough to prove the existence of idempotents. Now, a natural question is, maybe just assuming that every filter on the natural numbers is extended to an ultrafilter is enough to prove the existence of idempotents. But let me mention that behind this, to me, the most important point should be to find alternative, genuine, different proofs of the existence of idempotents. Since they are such central objects, having only one single procedure to prove their existence, I mean, it's not a good thing. Now, this notion of idempotency can be easily reformulated in more general model theoretic term, because what we have is a point with the property that whenever a formula is satisfied by that point, then also the property is also satisfied in a shift, but the shift by a number which again satisfies the same property. It's a tricky thing, but so my general, not precise question is the following: is there an alternative proof of the existence of these idempotent elements by using some typical machinery of model theory, producing in this way a really new proof of the existence of these objects? And it has been recently proved that as far as countable complete extension of Peano arithmetics, this is the case because we have a property that is actually equivalent to Hyndman's theorem. Now, another annoying property that we don't know about is about the fact that this U equivalence can be the identity in some non-standard model. Which means, are there models of non-standard analysis where different points have different one types? Now, in non-standard analysis, the language we are using is the richest possible. So here, types are ultrafilters. And the properties we have when reformulated in terms of ultrafilters is that one. If the image under two functions of the same ultrafilter of U are the same, then it means that the two functions agree almost everywhere. Now, this is still open in ZFC. It is a consistent property, but it is still open. It's unbelievable because it's such a basic, simple property about ultrafilters, but we do not know if this is a theorem of ZFC or not. And the last question is about the Pythagorean equation, which is a central thing in this area. And as you see, we know almost everything around this equation. So we recently, there was a paper on Nature about the longest proof ever, computer-assisted proof of the fact that for two colorings, that equation is partition regular, but not for the general case. And as you see, we know that x plus y equals z is partition regular. X squared plus y equals z is partition regular because of results by Sarkozy and Fürstenberg. X plus y equals z squared is not partition regular. X squared plus y squared equals z is not. I showed you before a short proof of that. X squared plus y equals z squared is partition regular proved by Mauro, but as I mentioned, this is also a straight corollary of the theorem that I mentioned before. And one can play a little bit with variables. In any case, if someone is finding a proof of this partition regularity, it would be nice. So as a final slide, let me do a commercial. We have a small meeting, of two-day meeting in Pisa, the 16th and 17th of February, about Ramsey theory of equations, so partition regularity of equations of any kind. Any of you is welcome to participate. And here is a list of references, especially the first one, if someone is interested, can serve as an introduction to what I said. Okay, thank you.
Are there questions?
Yes.
Do you know then what the effective content of that result is?
You can find out that you mean if you can actually find the finite partition you are talking about.
Like how many colors are involved, what, some information. From the fact that this is the proof, we need to look into the proof, or
I don't understand the question. You mean the non-standard argument I'm using?
proof can be proved in this way, does something effective follow from that proof? An effective result. As to in what way it's
I think so, because usually if you look carefully at the proof, you can actually.
No, I don't mean that. I mean by the sort of general, proof mining type method.
Oh.
A priori, what do you need to do?
No, I've never thought about that. It's an. Yes.
Yeah, so this iterated construction is a little bit like the iterated ultrapower. That can be.
Yes, but the so-called internal ultrapower construction.
Yes, but my question is, can you push this to the limit when, and if this is the case, we have something like an extender, internal extender. And then the reason that I ask you this question is it seems to me that those many open questions on partition properties or countable ordinals, perhaps within the range of your method.
Well, you can certainly iterate this, but if you take the limit, well, inside that limit, I mean, a model for this thing, to me, the simplest model is to take an elementary extension of the universe into itself, if you want to think in set theoretic terms. Now, this is, of course, not possible, but since we are working with non-standard things, we are dropping the foundation axiom, because star omega will be not well-founded. But in that context, you actually can have elementary extensions. So over there, you can iterate anything you want. So I'm not sure if this can be of any use, more than taking the limits. Yes?
Has anyone looked by your methods into systems of linear equations, homogeneous, to which one wants to find small, whatever that means, integer solutions? Things that in the philosophy are Zille's lemma, Borgheri's lemma, etc. Do you know anything like that? It seems to me that your methods would be quite appropriate.
But about partition regularity property, you mean? Because
Even yes.
well, of course, the next step, I mean, I just considered single equations, but of course, systems are, I mentioned a few of them, but we never looked into that direction. I mean, my point is that I'm sure there will be, I hope there will be smarter people than I am looking at these techniques and using them to produce new results. I'm pretty sure that since I was able to produce small new results, smarter people will be able to produce much nicer results. The techniques are really nice and really powerful. That's my point.
So in the position that every attributor or real numbers extends to the attributor.
Sorry, every? Say it again.
So I think you put something like it is sufficient to assume that every attributor on the rears extends to the attributors.
Yes.
Then you have Heidemann theorem.
No, I have idempotents.
Oh yes. But then the list, how much choice it uses? I'm wondering, does it answer some reverse math problems of Heidemann?
Well, that's a weak form of choice. Having every filter on the continuum to be extended to an ultrafilter is a weak form of choice. And that property is used in some sense, in a precise sense, to produce a choice function that choose one ultrafilter extending any ultrafilter on n. So if you have this property that every ultrafilter on the continuum can be, and every filter on the continuum can be extended to an ultrafilter on the continuum, you can define a function that take from the family of filters into the family of ultrafilters on n, so that every filter is mapped into an ultrafilter extending it. It can be of some interest, of course. For instance, even the property ZF plus there exists a non-principal ultrafilter on n. Is that enough to prove the existence of idempotents? But again, it's all about finding a new proof of the existence of idempotents if the result would be positive.